Hello, my name is John, and these are my teammates. And today we're going to talk about binary phases diagrams and development of microstructures in eutectic alloys. What is a eutectic reaction? In binary diagrams, we know that when changing the temperature, the structure of the system can change. And in some systems, when you cool the system, the reaction will be solid, and when you heat them, the opposite thing will happen. It will become liquid, and these cases are called eutectic reaction. And all the solid products of a eutectic system consist of two solid phases, alpha and beta phase. Some history. In the past, the majority solvers have been lead-tin alloys. These materials are reliable, inexpensive, have relatively low melting temperatures. The most common lead-tin solder composite is by 63 weight percentage of tin and 36 weight percentage of lead. And this is an example of the solid phase of a eutectic alloy. The alpha phase, which is the lead, is the dark part, and the light is the beta phase, which is the tin. This is a phase diagram. The alpha phase is mainly made out of copper, and it can have silver as solute or not silver at all, and the opposite for beta is mainly made out of silver. See solubility. As you increase the temperature, solubility increase until you reach the maximum solubility point for both alpha and beta. And this point is at 779 Celsius degrees. And after you increase the temperature more, the solubility will actually decrease. And the line that separates homogeneous and heterogeneous phases is called solvus line. And the line that separates solid and liquid phases are called solidus. This can be also called a solidus line, and also it's called eutectic line. And the line that separates homogeneous and heterogeneous liquids is called liquidus. And in here I'm gonna show you how to do the eutectic reaction equation for this specific phase diagram graph. So in one part, when it's heated, it will be liquid, and the liquid is 71.9 weight percentage of silver. And when you cool the system, you will all the opposite. When you heat it, it will go liquid. When you cool it, it will go solid. When it's solid, you will have two phases, the alpha and beta. The alpha phase is 8 weight percentage of silver plus beta, which is 91.2 weight percentage. And this is the equation for this phase diagram. Now I'm gonna pass it to my teammate, Guan Ling. Thank you.
All right. Hello, I'm Guanlin Zhao. I'm going to talk about development of microstructure in eutectic alloys for case 1 and case 2. So in case 1, here is a lead-tin alloys at composition C1. So it's at around 2% wet. So in here, in point A. So it's all liquid in here, and when the temperature going down, it moved to point D. The alpha phase comes out, and it's mixed with liquid. And when it's going down between 300 degree to 200 degree, the alpha phase all comes out and is full of alpha phase. And now we move to case 2, and the case 2 is the composition C2, so it's moved to a little bit to right, at around between 2 wet percentage to 18.3 wet percentage. So at here in point D, so it's all liquid in here, and the temperature going down when it's below 300 degree at point E. The alpha phase comes out and mixed with liquid, and when it's keep going down to point F, so at around 200 degree is all alpha phase in here, and when the temperature keep going down, the beta phase comes out and it's mixed with alpha phase. All right, I'm going to pass to my teammate, Mehdi.
Hi everyone, my name is Mati Kubat and I'm going to talk about case 3. So case 3 is on the 61.9 white percentage. As you can see on the top region is the liquid. It's only liquid phase, and if we cool down just below the eutectic point or eutectic temperature, we have transformation from liquid to alpha and beta phase. So we don't have any liquid. The alpha is 18.9 as you can see here, 18.3, sorry, and the beta phase is 97.8, as you can see as a patches. So this thing here is the microstructure. This resulted from this transformation is called eutectic microstructure. You can see this micrograph from the lead 10 eutectic microstructure. As you can see, the lamella are formed below the eutectic temperature. So the lamella eutectic structure is, so the lamellar formation is also shown here, representing the formation of eutectic structure for the lead 10 system. The direction of the diffusion of these things and the atom are indicated by blue, and the red arrows, as you can see here, and the utility growth direction is shown by the big red arrows. Let's move to case 4. Case 4 is the composition weight ratio is above 18.3 and between the 61.2 61.9, sorry, and as you can see here we have only liquid phase. If we cool it down just around this point, we have liquid and a few alpha particle. As we decrease temperature, the alpha particle will become bigger and just above the eutectic points, and if we go below the eutectic points, we have this is like patches of alpha and beta, and we have the alpha lamella, which is 18.3, and the beta is 97.8, And next is going to be John, who is going to be doing some calculation. Thanks.
Okay, so I'm gonna do an example to determine the mass fractions of alpha and beta phase at this percentage and at this specific temperature, at this weight percentage and at this specific temperature. So we're gonna find the mass fraction of alpha and beta, the primary alpha and eutectic microconstituents, and the mass fraction of eutectic alpha. So to find the mass fraction of alpha and beta, we use this formula, which is composite of beta, which is, so basically the between 25 and 90 and this point, which is, to find that point is 91.2 minus 25, which is 91.2 minus 25 over this section, or all this section. So this section is 91.2 minus 8. To 0.8. So if alpha is equal to 0.8, then beta should be equals to 0.2. You can either calculate it or you can use like subtract by 1 and get the result. Then we're gonna find the mass fraction of primary alpha with this formula again. So composite of the liquid, which is 71.9, minus 25. So basically this part over this whole part. So 71.9 minus 25 over 71.9 minus 8. This is equal to 0.733. And for the weight mass fraction of the eutectic microconstituent is, so 25 is here, minus 8, which is this part, over all this part. Okay, so 25 minus 8 over 71.9 minus 8 equals 0.266. And the mass fraction of eutectic alpha is whatever we got here minus whatever we got here. So 0.8 minus 0.733, which is equal to 0.067. Okay, so that was the calculation part. Thank you so much for paying attention in my presentation, and have a good one.